Electric potential or voltage. We started studying electricity with Coulomb's law. That gave us the force, the electric force between two charges, and we can call them big Q and little q. By assuming little q is a very small positive test charge and dividing the force by Q, we found the electric field due to the large charge. Quick little review on our hat. This is a vector whose magnitude is 1, and it points in a line for the force between two charges, and here it points in the direction of the electric field. It just recognizes the vector nature of electric field and force. Electric field is a property of the space surrounding the charge Q. More advanced physics courses call it a vector field. Since dividing out a little charge worked before when we came up with the definition of electric field, we're going to do it again. We're going to take the electric potential energy, which is a scalar, so there's no vector symbolism here, K, large Q, little q divided by R. We're going to divide out the little q. So voltage, or electric potential, both names work, is KQ over R. V is the voltage. It is measured, how about that, in volts. And in, again, more advanced physics courses, this will be a scalar field. It is a property of the space surrounding the large charge Q. Another way of looking at what we've done is we have removed the system that was required to define electric potential energy. Electric potential energy required at least two objects or a field in an object. We have now divided out one of the charges. We have this property of the space surrounding this charge Q, and it basically tells you how much potential energy is in each charge, and if the charges are moving, how much work per charge they can do on another system. Voltage is the electric potential energy per charge. So if we want to use units, we will have a volt, which is a unit of voltage, is a joules per coulomb. To make that a little bit more understandable, you can visualize a volt as a battery will add 1 joule of energy to every coulomb of charge that goes through the battery. Batteries are a source of electric potential. You've always known they had voltage, but now you know the physics behind it. Voltage is really an abbreviation for electric potential. What batteries do is they use chemical reactions to separate charges and put electrons in motion. Chemical energy is converted into electrical energy, and in the unit-on circuits we'll talk more about this. Despite the different size of these two batteries, right, here's a AA, here's a AAA, which is smaller, they both have the same voltage, 1.5 volts. That means that every electron that leaves each battery has the same electric potential, the same ability to do work, the same potential energy per charge. The AA battery just has more chemicals. It's bigger, so it can have more reactions, so it will last longer than a AAA battery. Using the definition of electric potential or voltage, we multiply both sides by Q, and we have this down here, and then realize that if you do work on a positive charge with an external force, the potential energy of that charge will increase. So positive work will be positive potential energy, positive charge times voltage.